this visual interface for creation of workflows, for automation of simulation, for creating quite comprehensive workflows with different tools inside, and to apply our algorithms for these simulations. What we will discuss today in this meeting is the mutual integration advantages. We see two main fields where we can work together with the Amesim software. First is the multidisciplinary optimization, when Amesim acts like a solver in pSeven workflow. Maybe not the only one, but one of them. So we can incorporate this Amesim into multidisciplinary study inside pSeven. We can solve optimization problems with our advanced algorithms, which are much more powerful than built in Amesim in many ways. We can connect other tools to make this study real multidisciplinary, like KD and KE, and we also can preserve the workflow as a run-ready tool and to share it with our colleagues and to use it as a ready solution. So here's the idea that the pSeven is kind of driver for different simulations, and it integrates in one chain and apply the optimization or other algorithms to study the model. The other part is the approximation models. pSeven has capabilities to build approximation models based on simulation data or maybe experimental data to replace these heavy computational models or table data to make the simulation faster and also to control accuracy in this simulation. And we can embed these models into Amesim like a Amesim block to create custom models for special cases or just to speed up the calculation. So this is two parts which we will discuss today in technical details. So like how to. So first part is the technical demonstration how we can set up an optimization problem in pSeven with the Amesim as a solver. We optimize the single cylinder engine to improve its performance and reduce its mass. This problem will be solved with pSeven optimization algorithm. So usage of the pSeven can bring you some advantages like advanced optimization algorithms to handle real engineering cases when we have large dimensionality with quite a great number of variables, a number of generic constraints can be up to 100, and also we can handle several objective functions, so it will be multi-objective optimization. And also we can handle noisy functions and constraints, and our algorithms are suited for also for large calculation times, which is important when we talk about CFD or some other calculations that are really time consuming. So we will integrate the Amesim with other tools to solve the multidisciplinary problem. And this problem is the one single cylinder engine optimization. This model was taken from Amesim demo. I can just show you where this is the Amesim help. Here it is under the libraries and the IFP engine. So here it is, a gasoline single-cylinder engine. This problem was taken because it's quite interesting, and it also has this very rich documentation in Amesim, so you can try to do it yourself, maybe, or just to show to the people who know the Amesim. I'm sure they are familiar with this demo. So this is the simulation of single-cylinder engine. Here's the cylinder, the intake system, the pipes with the airflow and the exhaust gases, and also this fuel mixing part. It has also some geometrical characteristics. Geometry, it's the stroke, it means the height of how deep piston goes inside the cylinder. It's the bore, the cylinder diameter, and some other geometrical characteristics, and also performance characteristics like mass flow, which is just the static mass flow rate of the fuel, the throttle, it's the area ratio for airway valve, and some control parameters, the exhaust valve opening time, the intake valve opening time, and the start of the injection angle, all in degrees, regarding to the engine cycle timing. So this is very nice, quite rich model to study. And the objective that we will take from this model is the engine torque, mean engine torque at the crankshaft. So how we can integrate the Amesim simulation into pSeven, this is a general idea. We will create the text file with input parameters based on Msm template. Then we will pass it to Amesim project, run it, and grab the output file, then parse it to get the results inside the pSeven. So this is the general scheme for integration with quite every tool that has this batch mode simulation capabilities. In order to make this chain possible, we should make some settings in Amesim project. It's made here under settings. We should add some export variables. This setup allows to create variables that will be accessible from the outside of Amesim via these text files. So we create the input parameters. I already named them. And this is geometrical part, the control part, the mass flow, and also the output parameters, the mean torque, and also volumetric efficiency. We will not use it in this simulation. You can just add them with this add button and just set up somehow. After the setup is done, in the project folder of Amesim, we can find these templates for output file with TPL extension, and also template for input file. Here it is, it's also TPL extension. We can take them to use in pSeven as a templates for our text block to set up the integration. So here's the main idea. We have the pSeven project with the files inside. We have this calculation model, and we also have this folder with templates. I placed it in a dedicated folder just to keep them easy accessible. So now we will try to make this integration scheme in real in pSeven project, just kind of live demo. So here we have the pSeven. We'll create a new workflow and then just made this integration. We will need a text block to create, I said text block, to create input file. So here it is, I just open it. This is the usual way to create the input file for any solver. We will need a template to set up the block. So I go to our templates folder and take this in file template from Amesim. Now you can see this template. It will allow us to set up the operation list to substitute the variables. So we will take this stroke. I just make it active and the system asks me for the variable to substitute here. I name it stroke and it's an input file. And now we have this commands for substitution and this variable to as a port of the block. It will take the value and put it some here in the file. We also will take ratio and bore and intake valve opening time and also the exhaust valve opening time and the start of ignition parameter pum pum and also mass flow and the throttle. So that's all. We have the full set of commands that were generated automatically and these variables. We can also put a test value just to see that I can play now. See, the stroke is now 11 as a test value. It doesn't affect on any values during the simulation, during the run, just a test value. And the output file is written to the port output. It will pass through the port to the next block. So just be ready. By the way, we can set this path as a local path to make the project easy to move from machine to machine or inside the operational system. So this is the input file. Then we want to run our simulation. So I just call this shell script block run. This is the interface. We will have two files, the in file with file name cylinder point in and the out file, it will be cylinder out. Cylinder is just the name of the Amesim project. So the command is pilot. It's a batch adapter for Amesim running in batch mode, and the argument will be just the project name. And we also need to set a sandbox. This is a folder where the block will be executed. It will be the folder with our models. Here it's calc. So we can just set it up also as a local path to make it easy to move. And the last part is to grab the results also with a text block. So we will get the file from the shell script and just parse it inside this block. So choose the template from our template folder. Here it is. It's only 2 lines here, and we will read this torque as a torque variable. Here it is, test value. So now we're ready to make the connections. The input text block will create our file. We will pass it to shell script. Here it is, output file to in file. Okay, now we're ready. Then the execution will be made, and the result file will be passed to our out text block to be parsed. Oh, that's my mistake. Out. I just didn't set the direction of the file. Here it is, direction is output, of course. Now we can connect them. So out file to the input. So this is the chain for running the simulation. Now we need to uplink the inputs and the outputs to the outside of the block. Just a list of them, ratio, boom, boom, and torque, I think is all. Just uplink, and now they are connected to the outside of the block, and we're ready to run. I just saved the workflow. So once again, what will be done here during the run, the parameters from the outside will be passed to the input text block. The text file will be created with these variables. It will be passed to the run block, which is shell script. It will execute the command, make the simulation, and then grab the result file and pass it to the parsing block here, and we will get the result at the end. So now we need to set the sum of this. Boom, boom, boom. I'm taking the boom, 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 and the throttle. So now we're ready to run. Just play this workflow and see what's happening. So the input file was created, the run block was launched. So hop, pop, pop. Oh, it's very nice thing. It was fail on standard error in the command line. It happened because the Amesim write his licensing info into the std error output. So we need to uncheck this button. Now the block wouldn't fail on this standard error output. You can see here there was a requesting license report in this standard error output, and the block considered it as a failure. So we need to uncheck this place. So we can do it one more time. So the run is complete. we got our value from the model. And this is how the single run workflow can be set up. This is the first part of the setting up of optimization problem. Now we have our tool to run simulation with fixed variable values. So going back here.
Maybe Anton, maybe you can check if it's okay for everybody.
Yeah, of course.
Did they understand clearly what is doing the workflow? So you can. Is it clear for everybody?
Hello?
Hello?
Karen, this is me. Karen.
Oh, maybe I try to mute you and then unmute you back. Maybe it will help. So is it clear what happened here?
Yeah.
The way we created this integration chain. Okay, I think we're ready to go further. So we have this single run workflow with the inputs and outputs. The next we will discuss is this optimization problem itself. So I tried to make this demonstration quite as rich as possible. So I set up the multi-objective problem with external KED model for this engine. So now we will have two objectives: the torque of the engine that we get from Amesim and the mass of this model that we will get from KED. Here it is SolidWorks, but of course it can be Creo, NX, CATIA. All of them are supported just in the same way. So we build this KED model, and it acts like external tool, not the Amesim, but some kind of other simulational tool. It can be not the KED, but the structural analysis simulation, or maybe thermal analysis, and all other possible tools to analyze the model. So here's this geometrical model. It's very simple, just to demonstrate the idea. We control it's through the same parameters that the model in Amesim. It's the piston diameter and the stroke, and also the connected things like crankshaft length and length of the rod. So here it is. It's very simple. It doesn't pretend to be a realistic one, but I try to make it quite interesting. So now we will create the workflow like this when we optimize the Amesim model and the KED as two different tools inside one workflow. I just save it. So go back to edit. What can we do now? We can create a new workflow. We will of course use the optimizer block to control this process, to guide this optimization workflow, and we will need this KED SolidWorks block. So to deal with our geometry model, and we also need this previously created single run for Amesim. One of the ways is just just copy the block from one workflow, the whole copy to another. It will take all the settings with it, and inside this composite block, the whole structure is preserved. It's one of the ways to create more complicated workflows with the previously set simple parts. So it's our composite block. It has, you can see, it has the inputs we set up previously and the torque as output. Now, as what for the KD, we just open the block and we will see the inside. The block is waiting for some KD model. It's taken from the project. It's also here in KD folder. By the way, I can also make it local. You see these local passes everywhere allow us to take the project all together and move it to another location, to another machine, and to share it with other people with no need to care about the absolute paths for the files. So now we have this project. We want to build our document tree. This is the building tree of the model with for all the sketches, the parts, the sorry, it's in Russian. It's just our Russian version of SolidWorks. What we will need here, we have global variables, especially for this demonstration. You can take them from the sketches, but also we can use this global variables list. Maybe it's even more simple. We will just check the dimensions that we want to control from outside. It's the bore, the piston diameter, the stroke, and the compression ratio. And they now created like variables for our block. We can also set the export for the model into the native KD format or for exchange formats, but in this case we don't need it. So we will, and of course we want to get the mass as an output. So we will pass the inputs, the model will be rebuilt, and then the mass will be taken as a result of the this block execution. So just that simple. Now we have this KD to get the mass from parameters. We have this Amesim simulation to get the torque from our parameters. And the last thing we want to set up is the optimizer itself. Is it okay? Is it clear enough how to deal with the KD in this workflow? I think it's quite straightforward. Okay. Now we go inside the optimizer block. This is the setup screen. We need to add our variables, objectives, and constraints, if any. In this case, we don't have constraints, so starting to create the optimization setup. So starting with engine control. The boundaries were taken just for example with no special meaning. So now it's now this is for the engine control. This is also for fuel control, mass flow, from very low to quite high, and the air control, also quite a wide range. And now for the geometry characteristics. It's bore, I think it's something about 70. The stroke, also quite a wide range, and the compression ratio is quite a hard thing to set this ratio in a proper way, because it's connected with the structural things like stress and deformation of the cylinder. So I think we are ready. Here we have 8 variables, and now we want to add the objective functions. They are mass here. The type is generic. It's not linear, not quadratic, but generic. And the cost type is expensive. I think it takes quite 10 seconds to rebuild the model. So let it be expensive. It will affect on the choice of algorithms for optimization inside our smart selection tool. So, and the last one is the torque of the engine, also generic and also expensive. You can see it's all the setup. You can also set the preset. It's expensive problem. All the setup you need for most cases to make the pSeven optimization algorithms working. So the variables and the objectives with the hints. Expensive is one of the most important hint possibilities, because it turns on the global search based on multi-objective surrogate-based optimization. When we create the approximation model inside the optimizer and improve it at each step to get our optimal point, or Pareto Frontier in this case, because we have these 2 objectives. So that's all you need. Maybe someone wants to also to control the number of calculations. It's also possible. It's maximum expensive iterations thing. I just make it a parameter here. So now we create the KD block, the Amesim simulation block, and the optimizer block. You can just connect them. Since the names are the same, the connection are quite automatic. And also here it's 8 inputs and the torque as the output. So now we're ready to run. We can just save it once again. Okay. So this is the way you can set up. Sorry, we have some problems here with the echo, so I'll just mute. This is how you can set up the optimization problem with this Amesim inside this block, and just to remind you, and the KD as an example of external tool. It can be other simulator, or maybe in-house solver, or just analytical function or something. It's just the way how you create the workflow that is quite simple, but incorporate two different simulation tools. Now we go to the run panel. We can see the run button and this maximum expensive iteration parameter that I just set up in Optimizer. We can set the exact number of calculations that Optimizer is allowed to perform in order to find the Pareto frontier. So that's all the things that should be set. We can just now play the workflow. It started, the optimizer, some hints, and just now we're waiting for 300 calculations will be done in KAD and Amesim. It can take an hour or about an hour. So now one can go have lunch, and when back the solution is already waiting for him here in the analyze panel. Here we can see the history of optimization with all the inputs and outputs stored here. Just can see the all 300. It's the history from the previous run, of course. We can just plot this two-dimensional plot in the axis torque versus mass to see the Pareto frontier we obtained. Just know that it's two objective optimization problem. So we have not the single solution, but the whole set of solutions. Pareto optimal, it means that you cannot improve one and keep the other. So all the points are inside this line. The torque have the minus sign, so the better is here, is to the left, and the mass, the lower mass, is of course to the bottom. The Pareto frontier allow the engineer to perform a study of opportunities. For example, here we can see that we can, between these 2 points, we can win in mass for about 100 grams, and we don't lose any torque with this between 2 points because it's just a vertical line. So it's kind of a tool for trade-off study, to study the possibilities, and we get this Pareto frontier with quite high resolution in only 300 evaluations. That's the way how you solve the optimization problem in pSeven, and how you can plot the results to analyze them. It's on one of the graphs available. You can also plot these parallel coordinates for all the optimizational iterations to study how to distribute over the parameters. For example, we can see that let us select the maximum torque. All of these points go to the maximum throttle. It's just kind of easy to understand idea. The more gas you gave, the more torque you get. And also the stroke and ratio is quite limited here for the maximum torque, but the bore can be quite any. Or for example, you can select the lowest mass, and you can see that the bore should be small and the stroke can be big in order to get you the torque that is near the Pareto frontier. So this is just a way you can study the results you get. You can also, for example, plot the scatter matrix for all the points. Here we can see, just a moment, Here you can see that the mass and the bore is tightly connected. So it's just the main variable that affect on the mass of the cylinder. For example, you can see that the throttle and the torque, here is this screen, are also very tightly connected, and the more throttle, the more torque you get. And also the correlations between functions, you can see that bore with mass is very highly correlated. It's just because of this that the model here, the bore is the diameter. The bore has the quadratic influence on mass, and the stroke has the linear influence on mass. So of course the quadratic is much more powerful than the linear. By the way, we can see that the model is rebuilding here. You see, it's changing because the optimization is going inside the pSeven, and on each iteration it rebuilt the model. So I think it's all for the first part. I go back here and I will go to the results. So it was the demonstration of this solution for multi-objective problem with KAD as one tool and Amesim as a main solver for engine performance. And as a result, we got this Pareto Frontier to provide us a way to compare different optimal points, to make this trade-off analysis, and only 300 iterations takes us to get to this result, or about an hour of real time. So this is, I think, the end of the first part about the optimization in pSeven with Amesim as an external simulator. If you have any questions, you can about this part, you can just ask them now. Yeah, just unlock everybody.
Okay.
So it's
to ask now. Hello.
hello, yeah.
So we have some questions now.
Oh, here, I see.
You can listen to me now.
So the questions.
I want to know the process of generate Msm input file, template file, the process of how you generate the Msm template file.
Okay. So
see clearly just now.
yeah, the Msm template file. The Msm is quite a powerful tool for study. So when we set these export variables here, when we set the variables that we can control from outside, these files are created automatically. So they will just be two files for this input parameters list with these export names. You see, you can just change them for any name you want. And these output parameters will also be in the file. So when I click save here, or just close, okay. Okay, I didn't change it. So and now in this folder, these files, they append automatically. I think I can just delete one of them and then go to Amesim, open this export setup, save it, close it, go back, and it will be again in place. You see?
Okay.
So it's made by Amesim. It's quite simple to use this way of integration with this tool.
So one question. This demo exists in Msm documentation or you make it yourself?
No, the simulation is the part of the Amesim demo. Here you can find I didn't change anything inside the physical models or how it works. I just take these parameters for the expert to control them from outside. That was done to make it possible to repeat it and to your site maybe, and to make it more easy to understand for people who are familiar with Amesim demo. In fact, I'm not a very big specialist in this mechatronic simulations, so it's quite complicated task to create interesting simulation model that is easy enough to understand and complicated enough to be interesting for study. So just the Amesim demo. But of course it's not included into the Amesim optimization demo. There are a couple of simple demos for optimization in Amesim. I think solutions, maybe platform. Here it is. The Amesim has built-in optimization solution, but it's really for the very simple problems. It's just local gradient methods, and so it can be used only for maybe preliminary study or some very tiny little problems. For serious multi-objective, multi-constraint problems with many variables, it is just not the case for this built-in optimization. So I think that's all questions for the optimization. So the second part is about the using the predictive models from pSeven in Amesim as a block of Amesim. So first, the motivation. Building approximations is one of the key features of pSeven algorithmic core. We have very rich set of algorithms for high dimensional data, for noisy data, for full factorial plans, or maybe for experiments with lack of data in several areas. Our algorithms allow to control the accuracy of models. We can construct models with data of different fidelity levels. So it's kind of a whole life inside these algorithms. And you can use them to replace heavy computational models or table data, for example, CFD, structural simulations of the model, or experimental data, and to build these predictive models, which are approximations, but they are very fast and they are quite accurate. And then you can embed them into the Amesim project, like an Amesim submodel, Amesim block, and use them in Amesim simulation. Another way, you can just replace the Amesim model with the approximation of this model to speed up the calculation. The approximations that we built, they are really fast. So it can speed up the simulation and bring it closer to real-time control maybe, or something like that. And of course it's the way to create custom models for special cases. For example, you have the data from experiment or from some kind of simulation, and for a particular model, and you also have this model on Amesim, so you can just easily build another block for your special problem and use it in Amesim. So this part doesn't have any interesting demonstration case, just a technical demo. So what should we do? We can build a model in pSeven and export it into a source file, source code, C language, and then we can use it in Amesim. It's a Amesim tool for creation the custom submodels as this code as a code of the submodel. So this is the way it can be made nowadays. I think I just show you again in real, so we can save it all. Stop for our optimization. I think it's no sense to wait to end. Close and open another project. It's boom. Where am I? Here it is. Msm Approx. It's just the pSeven projects that show the way how to build an approximation and export it in pSeven. So here it is. So we have no, it's not the one. Here it is. We have some data. It may be a solver data or experimental data. In this case, we have it stored in the text file, the CSV file. It is just the lift force coefficient versus the angle of attack. Just for example, it was scanned through. It's a very simple example, only one dimension, only one response. But just for demo. Now we want to pass it to the approximation builder block. It takes the X sample and F sample as inputs, and then create the approximation model that is also saved to disk and passed to this approx player block. The player block itself acts like a player. It takes the model and waits for inputs and returns the responses from the model. But in this case, it acts like the translator between the internal format of the approximation model and the export file. We can export it to here, just to C source code, to Max, and to MATLAB M file for further usage in projects. So once again, this workflow takes data, it splits it into inputs and responses, passes to the builder. The builder builds the model, and then the player acts like an export tool to get this C source file. Here it is on disk, I think. So just in the model, we have this model source C. What we can do next? We can go to Amesim, start the Amiset tool for creation of these custom blocks. Here it is. It's already preset for somehow. You can create the icon. It's the lift coefficient, CY. It takes an angle of attack as an input and returns the coefficient as an output. Only 2 ports. So this is the setting of the graphical interface of the block. And then we go here, it's the built-in editor for the submodel code. When you open it, it already have some preset for the model. We can set the title, the description, and so on. But we are interested in 2 places. Here we can insert our private code. It's just the model that we exported from pSeven. here is the section. So this is the part from the pSeven. It's quite big, so we can just go to the end. And so the end section is here. We have this node that we have one variable and one variable at port 2 as an angle of attack and degrees and so on. So on here we need to make some simple coding just to call this model to get the result. Of course it's quite complicated now, but it's allowed to made it in a solid way when you control all your memory leaks and variable definitions and so on. So now you can just compile the submodel. It's completed with no problems. And once again in Amesim, I just opened the demo where it is here. No. Here it is. It's just a very simple demonstration. So I just take this block. Now it's here on the library tree. You can see it's two of them even. You can take this block, give it some input, just a signal, rising signal, and to save it to the file maybe, just for technical demonstration. Now we go for simulation mode. We can run it, and it works. In fact, you can plot the result. So it's just the time and the meaning of lift coefficient from the model. See, it's how it can be done. Of course, this example is not very interesting because what can you do with this lift coefficient in the workflow? But if you have the pressure distribution maybe from some CFD tool, and you can use it for modeling of hydraulic system, for example, and so on. So the demo is technical, but the idea is very rich and powerful, because you can here it is. You can just replace heavy computations with these models and use them in Amesim simulation. The last part of this will be kind of future thing. The proper way to integrate with Amesim is to export our approximation models to functional mockup interface, and we're already working on it. We know about it. It's quite an industry standard for such model exchange. So I think in next month or two, the integration of pSeven approximation models into Amesim will be much more smooth and easy for the user.